academic license that enable you to use unlimited variable setting? Have you done this? Have you done? How many of you successfully get the academic license? Usually they respond to you within a day to provide. Not many? Okay. That's something I have imagined. So I have updated two files, which is FLPL and FLP solver. Okay, FLPL has a large set problem, so you cannot use without academic license. But FLP solver is a small set problem, so you can use Excel default solver without using what's best. Okay? But I will give you the first assignment by using academic license one. So anyhow, you have to install and then get the unlimited license. Okay? But if you can understand today's small set problem, I do not expect any difficulties to submit your first assignment by applying the same theories and same storyline. So that's something I will do in this week. Okay. So today's class session, the title is Distribution Center Location Decision. So there are various types of the decision making in logistics. The first one is start with the location decision. So in the logistics echelon, you have the facility, for example, warehouse, and then, for example, transport center or transport depot. So all sort of the facility should be considered the right location, as a right location. But the location problem set involves with many criteria, which involves the distance or number of the locations and so on. So there are kind of a framework to set up facility location. Okay? So in short, we call this as a FLP, in standard term, FLP. Facility location problem set. Okay? Facility location problem set. Okay, so facility location problem set. This is the map of the UK. For example, you know where your demand exists, and then to provide your product from a facility, you have to set up the right location of the facility, for example. Okay? So it is kind of a tree structure. So from a location, you provide your product. Okay? So that might be the multiple layer. So first one is a kind of a manufacturing facility, and from the manufacturing facility, you send the good to the distribution center, and then from the distribution center, you distribute the good to the customer's warehouse. So that is a typical B2B facility location, B2B facility structure. So as you all know, the location is indicated by red circle or blue circle. They should be located in the right place. Right place means it should be optimized. So optimization process applied to here to set up the right location. Okay? And another thing is that also not only the location but the number. For example, how many facility location, how many warehouses do we need to serve our customer? Because opening a facility also costs a huge investment, isn't it? So reducing the number of facility, number of warehouse would be also one of the optimization target in this type of stuff. Okay? So either reduce number of the location or maximize the number of the customers' demands by the fixed number of the warehouse. That is two different way of the optimization. So there are many strategies. So strategy means setting up the objective function. So I said in optimization we need three things. What was the first thing? Decision variability. Isn't it? What do we wanted to know? What do we wanted to get as an answer? In this case, its answer is the right location, geographical location, or number of the facility. Isn't it? And then objective function. Okay? Objective function is what do you want to achieve? Are you going to reduce the distance between center and then customer? That means average distance from the center to the demand. So that could be the one of the objective function. Okay. And then last one is constraint. Constraint is very important because we are studying the industrial subject. So you have to consider possible limitation in applying your theory into the practice. So for example, the maximum facility capacity that you can handle in one size of the warehouse is kept by certain volume or quantity, then that could be the constraint. If you have the kept warehouse capacity, then the number of warehouses could be different. Because you also have to consider how big the demand is, and then also at the same time you have to consider summing up all the demand served by this center is big enough to digest all the serving customers' demands. That could be the constraint, isn't it? So you have to consider possible constraint. Okay, and then also this is also business side. You also have to consider relevant cost factors. For example, running a warehouse here and here and here might be different. For example, area of the London, the land cost is much bigger than the land cost of the Liverpool somewhere, isn't it? So you have to consider average labor cost, then will be affected. That will affect your warehouse labor cost and then land cost. And of course, the distance is also very important because distance influence the traveling cost from center to the demand, and then also the service level. If your customer asks you 6 hours time window between the departure and then arrival, then you have to set up much densely populated warehouse. Otherwise, the distance is too far away comparing with the required distance. That means required service level. Okay? So that kind of things could be the constraint. Okay? The constraint part should be very detailed. Otherwise, your solution from the optimization process will not work. So that's the setup of this facilitation problem. So, largely speaking, there are some relationship between the number of facilities in the network and then the cost. And then the cost is comprised with the facility setup cost and transportation cost and inventory cost. Summing up the all cost that makes total logistic cost in the company's perspective. So for example, if you increase the number of facility, that means if you set up more and more warehouse inside of your network, distribution network, then of course you can expect that the facility cost increase linearly. Every warehouse you set up cost establishment cost. And at also same time, you have to run the safety stock for each warehouse. Okay, so each warehouse run some level of the safety stock. Safety stock means the stocks that can support the lead time and then uncertain order peak for each facility. So that also increase as well. But the transportation cost is also a little bit different. Because the transportation cost somewhat reduced up to the certain level and then again increase. So reduction can be explained because if you have the more and more warehouse, then the distance between demands and then the service center or facility reduced because you have a more warehouse. So there are potential routing that can be reduced. But after you pass through the optimal level of the number of facility, then it again increase. Why? There are some overlap routing for each other. So it is suboptimal situation. So by summing up the total, then you can calculate what is the optimal number of the facility, considering all possible cost factors. Okay? So that is just conceptual optimization things. So this is not enough. Okay? We are not sitting here to just understand this graph. Okay? So we need to think about much more detailed factors. Okay. This is the only table that I want to explain and then make you understand to today's session. So there are classification of the FLP. Okay. So the classification starts with the three different categories. The first category is a covering model, what we call as a covering model. Under the covering model, there are three types of the model. And then under the P-median model, there are P-median problem and capacitated P-median problem. And then P-center model, that is the P-center problem, and then capacitated P-center problem. You might see some pattern. One, and then capacitated one. One, and then capacitated one. Capacitated one is just a little bit tweak than the previous one by adding extra capacity that can be handled in the one unit facility. Okay? So you have to consider extra constraint next to the previous one. So this is capacity of PMP, capacity of PCP, capacity of MCLP. Okay? So it's a structural things. And then let's start from the covering problem set. The covering problem set has the objective function. I said objective function is important. Okay? So objective function is the what do you want to achieve in optimization, through the optimization. They want to achieve minimum number of the facilities. That means we do not have the fixed number of the facility. For example, the objective function is comprised with different cost factor. The first one is the demand point urgency, and then facility budget limit, and then public concern. Okay? So this is the perspective of the objective function, and under the facility budget limit, there are some criteria whether you have the fixed number of facility P or not. So objective function already telling us this is not fixed because I want to minimize. So number of facilities is not fixed, but I want to just minimize. I don't know how many, but I want to minimize it. That means number of facility in this problem set is not yet fixed. It's not applicable. Okay? Then the service level perspective, you have to think about desired service distance. That means I want to have the maximum distance between the service center and the service point. Service center, facility, and then demand. It should not be above or beyond the maximum distance. Why? Because that overrules the customer's request, customer's requirement. So that is the service level requirement, and then coverage for all demand points. So should I miss any customer? But that is important. It's two sides. One side is the number of facilities, and then the served demand. Should I have the all-inclusive customers demand points, or can I waive some of the customer from our service? That is the two factors. So here, applicable means I cannot waive any customer from our service network. At the same time, I want to minimize the number of facilities. Okay? So that is the LSCP, so location set covering problem set. And facility capacity upper bound is not yet applied. So this is related with capacity. Okay? Related with capacity. And then equality concerns. Equality concerns means, for example, you have the big customer and small customer. Okay? Probably you give more weight to the big customer, isn't it? That is quite natural in the business. But what about in the public sector? Can you respect the big city more than the small city? In public sector, you should have the equal concerns. One city is one city, one man is one man. Isn't it? Life is important for everyone, isn't it? So you have to understand, you have to apply the equality concept here. Okay? So I cannot discriminate any small demands through the optimization. So that is the factors over here. And then the same meaning is here. The equality concern can be implemented weighted by the demand side. So it is twice. Okay. So let's do the first things. That is just minimize the number of facility, and then you just switch the objective function from number of facility to coverage of service. So from the name of the objective function, you already can imagine you have some allowance to waive some customer. Okay? So my target is not covering the whole customer, but maximum customer. Okay? But the thing is that the fixed number of facility. That means I have a budget constraint. So the maximum budget I have is a 3 facility or 4 facility. Instead, I can reduce. I can waive some demand points through the optimization. So here you do not have the equality concern because you have to consider big customer because you want to maximize the number of demands or size of demands with the limited facility set, isn't it? So it is either fixed number of facility or either fixed the demand concerns, coverage of the all demands. So they do not they release the facility numbers constraint, but they still have the facility numbers constraint here. Okay. So, but still they all have the service constraint. That means between the distance between facility and then demand center has a maximum distance. That is the one. And another, so that is the covering model. And then let's move to the P-median model. P-median model. And P-median model is telling you that different objective function. So objective function here is to minimize the weighted average of distance. This is also what we call as a center of the gravity model. So that means you have to make a facility location that reduce the average, the weighted averages of the distance minimization. So here, of course, equality concern is now applicable because your warehouse, your facility will be closer to the peak customer because that is the weight of the that is the center of the gravity. Okay. And then variation of KMP is adding another capacity constraint over the facility capacity. So that is the one. Okay. And then here you have to provide all the customer coverage here. And the last one is that P-center program. P-center program. That is the different objective function. So we call it minimax. The distance. Minimax. What is the minimax? What is the definition of minimax? Minimax means minimize the worst case. Minimize the maximization. Minimize the maximum number. Okay? That means among the whole distance, you want to minimize the worst case scenario. So that means from the many set of the distance between facility and then demands, you might see that the maximum distance, which is isolated demand point, isn't it? So you have to reduce that isolation by setting up your facility a little bit closer to the isolated area. So that is exactly telling you the equality concept. Okay? No customer need to be discriminated by their location. So that is the equality concern part. And then that is realized by minimax distance. Okay, so that is the minimax distance. Okay, and they are dealing with the distance. So the distance is not fixed. So desired service distance is not fixed. Okay, but the fixed number of facility is applicable. And equality concern is applicable. Here, not applicable. P-center model has a equality concern. Okay. So this is the total structure of the facility location table set. Okay. And this is also not enough to understand the framework. You have to run by hand, by practice. Okay? So, the mathematical formulation starts to come up. So, first thing is the LSCP in a covering model. That means reducing the number of the facility center. So that the problem can be transformed as a mathematical form here. So I want to minimize xj. By the way, you have to define what is I and what is j. So I is set of demand node. So location will be constant. And then j is set of facility side. So location of the facility. That is j. And then what is distance ij? The distance between facility and then demand. And then dij, that could be many things. That depends on how your network looks like. Okay. And then you have the two decision variables, okay? X and Y. Previously you have the only one decision variable, isn't it? So now you have the two set of decision variables. That is y, I, j, and then x, j. Okay? That means both decision variable can tell you how your distribution network looks like. Okay? And especially xi, that is showing that is binary variable, binary decision variable. So 1 and j. 1 or 0. 1 means we locate facility at the site j. So what is j? Facility site. You have the candidate of the facility. Among them, which specific j has a really the facility? That is a decision, isn't it? So in one city j, whether you choose that site as a facility location or not, so that is coded by the binary variable 1 or 0. So 1 means setup, 0 means no setup. And then Yij means if I means the demand node, isn't it? I means the demand node. So demand node is served by the facility node J. So that is kind of connection here. That is network. That is I, isn't it? Okay. So whether this is Y, I, J. Okay. So from a facility site J, you can solve the demand point I, isn't it? So that is the arc of the network. We call this is node, facility node, customer node. Okay? And then this is arc. Arc means the line, connection, or link or arc. So that has to be also coded as a number, 1 or 0. There might be certain node which is not served by, for example, this is not served from site J, then Y I dash J should be 0, isn't it? And that should be 1 because this is a solved J. So if you make a matrix over Yij and Xj, you can delineate the network because that includes all the required information to have the structure of the network. Because you have the node information and you have the link information, isn't it? So collecting that information as a matrix that gives you how it looks like the network. So that is the important definition of the first problem set. And then I explain what is the Dij. So that is a physical distance between 2 points, isn't it? And Dc, that is the distance coverage. So maximum distance, quality related factor. So the maximum distance between the facility and then served customer demand should not be more than 10 kilometers or 20 kilometers. So there is a various quality related constraint. That is the DC, distance coverage. Okay. And then Ni is the set of the candidate, because there are many types of the demand. There are many types of the facility side that is not that does not satisfy distance coverage conditions. Okay, not every pair. There are many pairs. No? So there are I by J pairs. Okay, if you have the 100 node and then another 100 node, so there are 10,000s of the cases. But this is not always applicable. This cannot be. Some of them cannot be the candidate of the network because that doesn't satisfy the distance constraint conditions. Okay, so only the set of Ij that satisfies the distance condition is a candidate of the network link. Okay, so that is the definition of this one. And then what I wanted to achieve is I want to reduce the sum of xj, means there are possible value 1 or 0, isn't it? So when the CTJ is selected as a facility location, that gives you the 1 as a value, isn't it? And then you have to consider all the possible j, isn't it? Of course, you do not know which CT can be. So anyhow, if you sum up the xj, that is the number of the facility, isn't it? 1 means setup, 0 means no setup. So if you sum up xj, then that is the total number of the facility. So that is the here, and then j is included as a total j set. Okay, and then subjective to in short ST, S dot T. I want to achieve this objective function under the condition of this. Okay, so that is the what we call as a constraint. Okay, what we call as a constraint. Without this, 0. Minimization is 0. No setup, any others. That is the make no sense. That doesn't make any sense. So you have to set up the subjective function. And then xij should be bigger than 1. Oh, this is the reverse of A. Do you know what it means? that is the xj. That means all the customer side should be supported by any one of the sides, because I have the conditions of the coverage for all demand points. Okay, so every demand point should be served by any of the facility. Okay? So I cannot waive, I cannot omit or eliminate any demand point from our network. And xj is 1 to 0, 1, 1. And then yij should be smaller than, you know what is the, what it means? You know what it means? 2 bar. 2 bar. So, for example, you have the set of, for example, A, B, C, D. The set of the components of the group is 4, isn't it? So this is 4. Okay? So you do not know how many customers, but if you know the set of the dimensionals, so you know how many customers you have to serve. Okay? And then that is the number of the demand, total number of the demand. And then xj. That should be smaller than yij, sum of yij. It means, for example, if you do not set up any facility over the site j, then that is 0, isn't it? So it should be the 0. So 0 multiplied by size of I, that is 0, isn't it? So without setting up the warehouse over the city, you cannot serve that city. You cannot serve that area. So this constraint, this protect nonsense under the network. Without setting up the warehouse, how can you serve from that warehouse to the customer? You cannot, isn't it? So only after you set up your site over the site J, then you can start to serve from there to demand side. Okay? So that is the condition of this. Okay, so let's try to solve one example problem. So I said understanding complex concept is supported by the toy problem set. Okay? The toy problem set I wanted to share with you. Excel function here. FLP solver. Okay? Open. Can you see this? Okay. So I have a very cute small size of the set. Okay. I have the city name 1 to 5, and then among the city, I want to select one of the city as a facility city. Okay? So that means demand point can be facility point. Okay? So this is very simplified case and very so this is distance matrix. Okay? So I means demand area, J means facility side. Okay? From a facility side, you have to solve the demand area. Okay? And then the location from one city to themselves, it is zero. Isn't it? So city by city. So that's why I said this is very simplified problem. But in real life cases, which I will explain next class, really follow geographical location of the facility and then geographical location of the customer. But this is just to give you the idea of the facility location problem structure and framework. So I make this simplified cases. Okay. So this is the exactly diagonal. Of course, distance from city 1 to 2 the same as from city 2 to 1. Okay. So that is the demand. Okay. And then you have the quality limit. So quality limit means maximum distance between demand and facility in here 10 kilometers. So the pairs that is larger than 10 kilometers will be excluded from the candidate set. What was the candidate set? Candidate set? I explained the candidate set.
J.
Here, the candidate set. Okay? In a slide. Okay, so only if it is smaller than the 10 kilometer, then it is automatically calculated. Beyond that. Okay, so not many. Okay. And then you have the two decision variables, isn't it? Okay. So the first decision variable is the xj. So whether you set up the facility on that location, on that city or not, you have only 5 cities, isn't it? So x 1, 2, 3, 4, 5, and then this might be 1 or 0, 1 or 0, okay? And the binary variable. That is our first decision variable, isn't it? And then the link Yij, okay? That is matrix. So this matrix, this Yij matrix is the decision variable. Okay? So this might be 1 or 0, 1 or 0. Okay? If you interpret two matrices, then you can depict how your network looks like. Okay? And then the thing is that you need several constraints in it. So the constraint set here. So this is a facility. This is the column is location. Column is the demand side. Isn't it? So just imagine that you are resident of the city 1, okay? And you see your which facility will serve you, okay? I'm not sure which one would be 1 or 0, okay? But you do not need two facility to serve your city, isn't it? So some of the city, some of the link under the one demand side should be 1, not 0. should not be any number. You do not need two possibilities for one demand point, isn't it? So that's why it should be same as 1. Okay, so if you sum it up, then that should be the 1, same as the 1. And that apply for every possible demand. Okay? So that is the perspective of the demand side. Okay? And then the last constraint that you have to remember is the lift side. So, for example, here, this is your decision variable, isn't it? So if you decide to set up your facility on the first city, then there is 1, isn't it? And then 1 multiply with the number of city, which is 5. That is the maximum service demand point from one facility. You understand? So rho means the facility view. Okay? I do not know which city I will set up the facility, but at once I set up the facility over here, then the sum of the row means the number of cities that I serve from that city, that facility, isn't it? So this is the view of the facility. This is the view of the demand. Okay? So if you sum it up, then this is the maximum city to serve. That is not that important. More importantly, if you do not set up the facility here, then there is 0, isn't it? So if you multiply 0 by 5, that is 0, isn't it? So if you sum up the total number of the city served from that facility, should be smaller than 0. That means small or equal to 0. That means quite natural. Without setting up the facility over there, you cannot serve any city from that facility. Okay? So that is the conditions that I mentioned in the last moment of the slide. I said this. And then this one is the single facility is required to have the one service. Okay? And what is missing? Still missing? What is still missing? So, how do we implement the service constraint? That means we already calculate possible Nij, isn't it? By the quadratic limit. How can we apply that condition into here? How can we? So, do you know sum product? menu sum product, isn't it? Isn't it? Sum product. The sum product is multiplication of this one and this one plus multiplication of this one, this one, this one. Why do we need it? Because the link which is out of our candidate should be excluded, isn't it? So if it is a 0, then although you have the 1 here, the total sum of them is 0, isn't it? Because this is the only possible pairs, only possible compositions that I can apply as a candidate, because we have the clear distance factors here, isn't it? So we should not just sum it up. We should sum the composition of the candidate that satisfy the distance conditions. So that's why I use sum product instead of just sum. Okay? So you need to, this is what we call as a handle. You see something here, and then you can just drag it, then the same things will be applied. Okay? Any question? Okay, so then we meet the all conditions. Okay? See, this is multiplication of the 5. 5 means this is 5 in this case, isn't it? So 5 here. So this is next city. So if it is a 0, then it is automatically 0. Okay? And then this is the sum of the city. Okay? And then objective function is the sum of your x variable. So there is the sum of your xj. Xj could be 1 or 0. I don't know what. Whether it is filled by 1 or 0, that computer decide. But anyhow, you have to sum it. Sum it up. Okay? And then okay, then you are ready to optimize. Okay? And then to optimize, you need to run the solver. Can you go to here? Can you see the solver? Huh? You don't need to install any software to run solver. Only things that you have to set up to run the solver is the turn it on in the Excel option menu that you can see. Is there anyone who cannot see the solver? So if I repeat again, then you go to the options and then go to the here, and then here, Excel adding in here, and then you need to check solver. If it is done like this, then you cannot see the solver. Okay? So you have to make sure this option is checked, and then here. Then you can see this menu. Okay? And then run it up. And then there are some fields you have to fill in. they are asking you, sorry for the language issues here. Next time I will change it in English. Okay? So they are asking you, what is your objective function? I said, you have to set up objective function, decision variable, and constraint. Okay? So for me, objective function is the number of the location, isn't it? That is sum of the xj. So you have to point out the set. Okay? And then x variable, and then decision variable. So they ask you which cell can I change out? That means among the many candidate cells, what number, what composition would be exactly the one that you are looking for? That is the decision variable answer. Okay? So they are asking you what is your decision variable? And the decision variable here is this one and this one, isn't it? Okay, so 5 by 5 matrix and then 1 by 5 matrix. Okay, and then between them you have to use the comma, because you have a multiple matrix as a decision variable. So to split it, just use comma. Okay, so comma here, and then you have the constraint set. So the first constraint means C and J 14. C14, C14 here. 14, that is the bigger than okay. So this condition is a little bit overlap with my sum product. You know why? Because you can set up any number here in x, isn't it? But that should be kept by here. That means if it is a 0, then only thing that you can apply here is 0. Okay? If it is a 1, then you can apply 1 or 0. Okay? So you fix the value that you can insert here or not. So that is the same meaning of the product sum that I apply here. Okay? Anyhow, if I product sum, then it is automatically eliminate excluded cases, but there's a two way. So now I understand why there was still the sum instead of the product sum, sum product. And the second thing is that C22, C22 to C26. So that is a matrix. So Yij matrix, that is the binary number. So 1 or 0. Okay? And the same things for the K20 to K26, that is the Xj matrix. That is also binary number, isn't it? Okay? And then this is the comparison of this cell and this cell. So the sum of the facility to serve one city should be 1. I need a single facility to get the service for each city. Okay? So that explain here, and then here also explain the total number of the cities served by one facility is equal or smaller than Ixj, I multiply xj. So that is already calculated. This is I multiply the size of I multiplied by xj. Okay? So this one should be smaller than this one. This condition. Okay? So everything is in. Okay? And then the last one that I have to apply here is the solutions. There are two different types of optimization. One is the linear programming and non-linear programming. The linear programming include only the linear non-linearity between the decision variables and then constraint and objective function. So in this case, we cannot see any non-linearity. So we just use simple linear programming. LP means linear programming. But if that includes minimax, for example, minimax, you need 2 times of a comparison. First to calculate the maximum, and then again minimization. Maximization of the minimization of the maximization. That is non-linearity. So in that cases, you cannot solve the answer by using linear. You have to use non-linear solution. Okay. Okay. So. Okay. So this changes, isn't it? Can you see? Excel to give you immediately the answer. Okay. See, let's see. What is the decision? I have to select. I have to set up the facility for city 3, 4, 5. Okay. And the total number of the cities, total number of the facility that I get from the optimization is 3. Because sum of this is 3. Okay. And then I do not miss any demanded point through the solution. So city 1 is solved by city 5. City 2 is solved by city 3. And so on and so on. So this is exactly 1. And then the facility that has been set up in the city 3 solved the 2 city. That is smaller than the 5. But if you do not set up any facility in the city 1, that is automatically 0. That is 0, and that is multiplied to the number here, 0. So the only the answer that you can set up here is 0. And 0, you cannot have anything in 1. All should be the 0, 0, 0. Otherwise, that is will not be the 0. Okay? So, like this. Everyone has the same answer or not? Huh? Some of you might not have the same answer. Why? Because as long as the objective function gives you the same answer, in this case, my objective function is the 3, isn't it? As long as it gives you the 3, the solution said this is satisfied, this is solved. But I'm pretty sure that you cannot have the 2 as your objective function. But as long as you have the 1, 3, then that is the answer. You should not care about this. So that is the typically the problematic multi-solution for one objective function. That is typically the problem of the non-linearity, non-linear optimization. So, but this is a linear problem set. So that is the okay. Any question? Any question? Okay, then let's take a 10 minutes break and then.